Without any planning at all, I just created this. From stone tools to space stations, human engineering has relied on planning. Imagine the result, then design and build it in steps. And how unnatural! Because nature doesn't begin with a blueprint, it builds through countless small actions that gradually form something greater. And now Penn researchers are going au naturel, and you won't believe what they came up with. Certain insects like bees build complex structures without any central planning. Instead, they rely on simple cues and collective behavior to guide construction. Researchers at Penn Engineering have now created mathematical rules that enable virtual swarms of tiny robots to mimic this behavior. In simulations, the robots assembled honeycomb-like structures without following or even understanding a predetermined plan. Robots that don't understand. I like that. It's a novel approach that could pave the way for a transformative shift in manufacturing. Each robot simply reacts to its surroundings. Since no individual robot needs to grasp the overall design, construction can continue even if some fail or veer off course. By having all robots operate in parallel rather than sequentially, the system can achieve higher speed and improve fault tolerance. The team has built some early prototypes, but a full robot swarm isn't quite there yet. And in order to build such bots, where do you go for parts? Mouser Electronics, of course. Omron Industrial Automation's E3NXCA color fiber amplifier units deliver reliable color mark detection for both standard and challenging environments. They accurately detect subtle color differences and maintain stability during lot changes. Featuring a high luminance white LED combined with smart noise reduction, these units enhance light intensity while minimizing noise. Detected RGB data is displayed on the unit and can be sent to the host in real time. Smart tuning settings enable automatic adjustment of light intensity and detection thresholds for optimal performance. To learn more, head over to mouser.com today or click the link below. Calculating is part of planning. But what happens when you can't just use the ohm setting to measure resistance in solid-state or AC devices? To explain, we present David's Corner.
Thanks, Andy. When it comes to measuring device resistance, it's usually a pretty easy process. You just take your multimeter, change the dial to the ohms or the resistance setting and measure. Problem comes in with AC devices or devices that are consuming power. If they're not plugged in, we can't simply measure the resistance. So what we have to do instead is a creative process using a couple of measurements and some math. First, we're going to measure the supply voltage. Now for AC devices, that's usually around 100 to 120 volts, but it can be a voltage either AC or DC for really any device. The next step that we need to do, which sometimes can be done with the multimeter, is to be able to measure the current. Now the current is a value in amps or milliamps. The math comes in with Ohm's law. To calculate our resistance when we can't directly measure it, we have to remember R equals V over I. So we take the voltage that we measured, either AC or DC, divide it by the current that we measured in either amps or milliamps or the appropriate value, and by dividing those, R equals V over I, we can figure out exactly what the device resistance or impedance is so that in future situations, we can expect and predict how much current the device is going to use. Andy, back to you.
Are you a smart byte or smart bit? Let's find out in our control automation quiz, Smart Bit. In our Smart Bit quiz, you must match the right answer to its question in less than 3 seconds. The questions are scored using actuator output percentage, and today we'll be testing your knowledge on networks, star versus ring, plus a window washing robot named Squigly. At the end, you'll see if you're a smart byte or smart bit. Let's begin with our first question on networks for 25%. In which topology does a single device failure not necessarily disrupt the entire network? Is it A, star, or B, ring? The correct answer is A, star. In a star topology, each device connects independently to a central hub. If one device or cable fails, only that device is effective. In a ring, failure of one device or link can disrupt the entire network unless there are redundant paths. Okay, let's move on to our next 25% question. Which topology typically experiences higher latency due to token passing? Is it A, star, or B, ring? The correct answer is B, ring. Ring networks often use token passing to control transmission, which can add delay as the token circulates. Star networks generally allow direct communication via the hub, reducing latency. Okay, now it's time to ask questions about our fearless high-rise window washing robot, Squigly. The first question is worth 25%. Squigly's path planning module detects an unexpected pattern of dirt accumulation requiring modified cleaning trajectories. Which approach optimizes cleaning efficiency while minimizing mechanical wear? Is it A, increase cleaning speed uniformly across entire surface, or B, adjust speed and path for deeper cleaning on heavily soiled areas? And the answer is B, adjust speed and path for deeper cleaning on heavily soiled areas. Targeted cleaning saves time and reduces wear by not overworking clean areas. Okay, final question worth 25%. Oh no! Squigly slipped on some bird poop and fell 20 stories to the ground. After the fall, analysis shows that Squigly did not alert operators in time. What communication protocol feature should be added to prevent silent failures? Is it A, limit data transmission to save bandwidth, or B, implement heartbeat signals and escalation alerts when anomalies persist? And the answer is B, implement heartbeat signals and escalation alerts when anomalies persist. Heartbeat signals confirm the robot is alive and communicating. But what happened to Squigly? Well, when an officer arrived at the scene, he asked Squigly, "What happened here?" And Squigly replied, "I don't know. I just got here myself." Ready for more? You can have another try by clicking the link on your screen. Thanks for tuning in, and we'll see you next time.